Greetings, fellow people of the soil. Today we're going to talk about Hopkins' rule of the halves. These are my rules, and I've kind of come up with them. Hopefully, they may help make some sense of the soil, water, plant, water relations world. It's important to understand these principles as we try to understand drainage and irrigation. So here we go. We'll talk about these soil moisture rules. So in basic soil science, we kind of teach this that half of the soil is solid material, half of it is pore space. If you have particle sizes, particles in the soil, minerals, they almost all have a density of about 2.6, 2.7 grams per cubic centimeter. And it's surprising. It doesn't matter what's quartz or whatever. Most of them have somewhere in that range, which means that if half of it is a solid space, that gives you a bulk density, which includes the pore space, of about 1.3 grams per cubic centimeter. So if the ideal world was really true, we would have these bulk densities. The reality is we rarely see a bulk density of 1.3. We see them typically much higher. So, when we throw in the reality of the thing, we see that it can be different. If we throw organic matter in, it makes it a little more accurate. Because we do have some organic matter, but even this, kind of textbook 5% is a little bit inaccurate. We don't usually see organic matter levels that high. Much more common for organic matter to be about 4%. If I do an analysis and it's 4%, that's on a dry matter basis. So that means it's about 2% of the total would be more realistic for the average soil, which is kind of why it's ignored in a lot of these discussions to kind of simplify things, but if we're trying to be accurate. So here's one example that is even more accurate, especially in the urban landscape. Typically these soils are not 50-50. They're more compacted usually because of traffic or tillage, and we get bulk densities that are higher. If I have a bulk density of 1.5, 1.6, I'm actually probably okay. 1.6 might be a little high, but 1.5 is pretty good. But if I have, here's one with 1.55, you can see that I've got less total pore space and I've got more total solid material. So if we kind of look at this here on the left, the one I just showed you, if we made it really compacted, the one on the right, that's got a bulk density of about 1.8 grams per cubic centimeter. That is extremely compacted, very difficult to move water into and through the soil. Plants are going to struggle, maybe even die when I'm that high. So if you see a high traffic area where plants are not going well, it could be that kind of a bulk density. But you can see it also affects the pore spaces and the total pore space. So that's important to realize. Now let's kind of go back to this textbook example. The other thing we kind of lie about, and we like to lie, when we say the soil is saturated, it's not usually really saturated. There's still some pores that have a little bit of oxygen in them. It's really impossible to drive the air totally out of the soil unless it just sits there with water on it for a long time, because there's these little pockets of air. So, this is kind of, the more reality, me being truthful today, we've usually got at least a little bit of air in there. So let's kind of get back to the generalization here of this 50-50 thing. If we had going back to this one, if we had a textbook example of saturation, this is what it would look like with all the pores sort of filled with the soil, filled with water. And after about 24 hours, we lose what we call the gravitational water. Gravity is able to push water through the macropores because the soil doesn't really have much of a hold on the water that's out in the middle of those big pores. And so it pushes it through. And so after about 24 hours, we lose that gravitational water. And we like to say about half of it is gone. Half of that water is gone. And we're down to what we call field capacity. After plants and the sun kind of do their job, we get to what we call the permanent wilting point, where plants, even if I water them, they're no longer going to be able to bounce back. Another lie. Now it's true for the species that was used to develop that point, which was sunflower. The scientists that worked on that, figured out the point at which sunflowers wouldn't rebound, once you added more water to them. So he called that the permanent wilting point. The fact is that species vary. Some species are going to be more or less tolerant, but we have that definition. It's a set point based on soil moisture tension. And so, and it's about half. It's about half of the field capacity is the permanent wilting point. Now, although the plants can continue to take up water, they do begin to have moisture stress at about that point. And so this graph represents, the water that's being taken up to that point. In other words, we don't want to go all the way to the permanent wilting point. If I'm growing sunflowers, that would be dumb. I would have lost my sunflowers. And other plants typically are showing stress at that point too. So usually we only want to lose about half of the plant available water before we try to put some irrigation water on or hope it rains. So what is the rule of the halves? Here we go. 50%, half of the pore space is water, and at saturation, it's all full. Again, not totally true, but for the point of learning today, half. About half of that is the what we would call the drainable gravitational water. The other half is non-drainable water that's held by the soil against drainage because of the forces of adhesion and cohesion that exert a tremendous force on that water and keep it from going. That's typically the water that's in the micropores, water that's really close to the soil. About half of that non-drainable water is what we would call plant available water. That's this guy right here. And then the other half is not plant available, or what we call hygroscopic water. So again, we're going halvesies. Another halvesies, if we took half of the plant available water, is what we would call the depletable water. The water that we can use really to provide for plants. If we start getting into this water here, this is the stress water. It's like, well, I can still take up some water, but my plants are starting to show some stress. So this is kind of the summary of the rule of halves laid out right here for you. Again, I think it's not perfect, but it's a good visualization of what we do. And it's important to understand this because then I can start doing some estimates on irrigation and drainage. So for example, let's say I have a turf grass with a pretty healthy root zone of about 8 inches. So mowed grass is typically, a little, we're lucky if we're at 8 inches, but let's just, for the sake of example, let's assume we got 8 inches. We're really good managers. So if we kind of stack it all up in terms of inches, which is sort of how we think of water in the soil, about half of it would be solid material, about 4 inches. And the other 4 inches would be pore space. And if it was saturated, it would be basically full of water, of 4 inches of water. So about 2 inches of that is going to be the gravitational water, right? And now the plants are going to be able to utilize that during that 24-hour period. They're taking up water, but we actually don't call that plant available water. The plant available water is between the field capacity, the permanent wilting point, okay? But again, it's a little bit of that's a confusion sometimes that happens when we are looking at irrigation scheduling. We forget about that day where we had free water during when it's losing its gravitational water. Now I got about 2 inches of this water that is not gravitational. About half of that is the hygroscopic water that plants can't really get to, which is 1 inch. And then the other inch is what is my plant available water. So if I were to ask you, what's the plant available water and how many inches is that in this example, it's 1 inch of plant available water. However, only half of that is what I would call my non-stress water, the water that my depletable water is what we call it. I'm going to want to operate. If I'm managing plants, I'm typically wanting to operate in this area here. If I'm irrigating, I'm going to irrigate up to this point, to where I'm not losing a bunch of water through leaching. And then I'm going to try to turn on the irrigation system when I've used about half. So in other words, if I'm irrigating this particular scenario, I'm going to wait until I lose about a ½ inch, and then I'm going to put on about a ½ inch of water. That's a pretty typical scenario. And let's say it's, hot day in July in Provo, Utah. My ET rates, ET is evapotranspiration, they can be 0.25 inches per day, that's pretty high. It's a hot day. So I would have to irrigate, every other day in order to manage this in this way, assuming the ideals, and again, that's not always the ideal, but this is hopefully a good explanation for you. How accurate is this again? Well, it's really not completely accurate. There are rules of thumb, which are helpful. It's good to have rules of thumb. So we can kind of understand the concepts and approximate and get a starting point when we're trying to figure things out. But soils vary. They vary in mineral and organic matter levels. They vary in texture. They vary in structure and a bunch of other things. Plants vary in root depth. I gave an example of a shallow root zone. A lot of plants root much more deeply than that. They vary in their root architecture and their efficiency. Potatoes are way more inefficient, than say pothos. Like my pothos plant in my office, man, I can take that thing down. It's losing its leaves, turn them black, and I throw a little water on it, and it'll pop right back. If I do that potato, if it even survives, I'm going to have ugly potatoes. So some plants more sensitive than others. Water use efficiency, drought tolerance, all of these things can be factors that would mean I would have to apply more or less irrigation water. So these rules of thumb are good. They're good approximations. They are. It's helpful, but we're just trying to teach you a little more advanced science here. But obviously, there's slight differences for each unique situation. For example, here's some different plants. These are crop plants. And we study crop plants more than we study other plants. We have lots of data on all of these because they're so important in terms of us eating. We like to eat, especially some of us. But you see that, at the point where like early in the year, alfalfa, yeah, it's got that 50% rule, where we can deplete about 50% of the plant available water. Corn is kind of the same way. Potatoes, a weakling. It can only go down to about 65% before it gets in trouble. Beans and onions are about 60%. And then that changes. Late in the year, the onions get worse than the potatoes. So that's really complex. Now, if I'm a professional farmer, potato grower, or an onion grower, I really need to know that stuff. If I'm growing onions and potatoes in the same tiny space in my garden, I'm not really irrigating that precisely. Hopefully I'm getting close, but the fact is that when we're really good at irrigation, we need to know these kinds of things. So of course things can change with atypical soils, but one of these things is a histosol. This is very, very different. Organic matter alters the water holding capacity, bulk density, structure. This is all going to affect the proportional levels of each of those water fractions that I showed you in those other slides. So a histosol would be an example of kind of an extreme soil. And remember, a histosol is something that has at least 20% organic matter, which is really high compared to the average soil. So we get a little different number there. So for example, if we looked at a histosol, it might only be 40%. It might be 60% pore space. And then it changes all the numbers. So we kind of have to understand our soils. The rules of thumb, the rule of halves is helpful, but again, it's just a starting point. So thank you very much.